Hello everyone, welcome to PYHPC SC20. I'm Vibata Bacon. I'll be presenting data engineering for HPC with Python. I'm a fifth-year PhD student from Indiana University Bloomington. My thesis advisor is Professor Jeffrey Fox. Let's get started. These are the authors contributed for this paper. The presentation outline is as follows. First, we'll be focusing on the data engineering and machine learning deep learning workflows. Then we focus on the state-of-the-art hardware and software stack. Next, we state the challenges in data engineering. Then we discuss the Python stack with the data engineering. Next, we discuss our solution to these challenges with PyCylon. Finally, we discuss the performance comparison with existing data engineering frameworks. Let's take a look at the data analytics workflow. The data analytics workflow starts with the raw data. The raw data is processed and sharded with distributed computation. MLDL training consumes such processed data. After training, models are evaluated. Following a successful evaluation, new data is post-processed using the evaluated model. Finally, the models are released for general-purpose usage. In this diagram, we showcase how each component in the data analytics workflow can be integrated with the Jupyter-centric system. Now we know the data analytics workflow. Let's focus on the data engineering component of the data analytics workflow. Data engineering is formulating structured data from raw data. Here, data extract, transform, and loading mechanism plays a vital role in formulating structured data. ETL pipeline has a vital prerequisite for many machine learning and deep learning workloads. Efficient data extraction and transformation plays a major role in an efficient MLDL workflow. In loading data from data engineering framework to MLDL framework, data must be converted to a numeric format understood by these systems. The state-of-the-art conversion of processed structured data into numerical and categorical formats are done by using pandas or NumPy. This is the place where overlap of data engineering and data analytics exists. With the expansion of big data, it's vital to design efficient data engineering frameworks to enable efficient and effective machine learning and deep learning workflows. Two ecosystems. The existing data engineering frameworks for big data are mainly written in Java, and they were mostly contributed from the enterprise application developers. Apache Spark, Flink, Hadoop, Beam, and Twister2 play a major role in processing such big datasets. This is the first ecosystem. Let's focus on the next ecosystem. The MLDL frameworks are often available in Python, though the compute kernels are written in C++ for better performance. PyTorch, TensorFlow, and Keras are some of the widely used data analytic frameworks. To seamlessly integrate with Python-based MLDL frameworks, frameworks like Dask, Modin, Pandas, and cuDF were the main contribution from the Python community. These tools are widely used in academic research and industrial research. When it comes to scalability and efficient data engineering, the big data frameworks are still in the front. But these two different ecosystems are not seamlessly coupled, and we observe some performance issues when consuming HPC hardware. We discussed the software stack, and now let's focus on the hardware stack. Focusing on modern data science clusters, CPU clusters can be recognized as the heavily used clusters for data engineering workloads. GPU clusters are widely used for data analytics workloads in machine learning and deep learning frameworks. In addition, there are accelerated hardware specially designed for deep learning workloads. For instance, TPU and FPGAs can be denoted. With large deep learning models, distributed training becomes a trivial requirement. To provide efficient data movement across thousands of machines, high-performance networks also become a vital factor. To facilitate the requirement of data engineers and data scientists, cloud infrastructure is also being reinforced for efficient workflows. With evolving MLDL applications, HPC clusters are also being upgraded. IUB Grade 200 is one such supercomputer. So far we discussed the data analytics workflow, data engineering, software and hardware solutions. Now let's take a look at challenges in data engineering. Since we discussed the two ecosystems a while ago, it's obvious that one of the main challenges is lack of seamless integration between high-performance big data engineering and MLDL workloads. Also, existing data engineering frameworks have some barriers in consuming HPC resources in providing efficient data pipelines. Gaining better scalability in data engineering to match up with the accelerated MLDL workloads is another challenge. Now we know the challenges in data engineering. Let's focus on understanding why Python becomes a key. Python is the favorite in data analytics frameworks like PyTorch and TensorFlow. Since data analytics is the main reason for data engineering frameworks must also support Python. PySpark, Modin, Dask and Pandas are such implementations. The main reason for using Python is the high productivity in model prototyping. But Python is not well known for high performance. To overcome this issue, high-performance kernels need to be written in languages like Fortran and C++ and wrapped with Python. For wrapping high-performance kernels, Cython and PyBind 11 comes in handy. In our research, we use Cython to write efficient Python bindings. Now we know the challenges in data engineering, and we know why Python plays a major role in data engineering and data analytics. To understand why Cylon was created, let's take a look at the Twisted2 project that we created some time back. Twisted2 was designed to bridge the gap between the big data systems and data analytics systems. First-class integration with the industry data flow systems like Apache Beam was one of our key goals. Apache Beam supports major big data frameworks such as Apache Spark and Apache Flink, and Twisted2 recently joined the family. But we observed some limitations in JVM-based implementations. Difficult to seamlessly integrate with Python frameworks is one of the main issues. But we observed that the best practice is to write data compute kernels that can be used everywhere. For this, we'll be focusing on writing kernels on C++. Thus, we developed the framework Cylon with a C++ core and exposed the APIs in Python and Java. With Python, we have an API called PyCylon, and for Java, we have an API called JCylon. And these libraries can be used to improve the performance in big data engineering in Python environments and Java environments. Here are some of the benchmarks we did on a couple of machine learning and data analytics algorithms. As you can see from the results, Twisted2 performs relatively better than Apache Spark while performing close to MPI. So far we discussed the challenges in data engineering, and then we discussed the motivation for Cylon. Now let's take a look at some of our suggestions to solve these problems. Rich data engineering APIs with high performance are lacking in the existing solutions. For big data processing, it's a must to have distributed high performance kernels. In our research, we use MPI along with high performance data compute kernels written in C++. Here we carry out heavy data engineering workloads in HPC hardware. Our data engineering kernels are available to be used as a library or a framework. When using as a library, existing frameworks like Modin and Pandas can be reinforced to run faster. We are currently working on integrating our research outcome to Modin. Also, our research outcome is available as a framework to be used in HPC environments along with other HPC resources. Here, the distributed memory computation is a vital factor when crunching large datasets across hundreds of machines. Our big data system contains distributed memory kernels provided for a BSP-like programming model for data engineers. The code written will be very similar to the code written in Pandas, Modin, or PySpark, but our research outcome provides much faster response. Next, let me elaborate how PyCylon can be used for data engineering. Since PyCylon can be used as a framework or a library, it can be used to reinforce the existing data engineering solutions. And since our kernels are exposed in a Python API, MLDL code can be effortlessly integrated with our data engineering solution. Also, we pay a close attention towards data representation. We adopt a columnar data representation format by using Apache Arrow kernels in the core of our compute kernels. This allows the seamless integration among data engineering data structures like data frames and data tables, and data analytics data structures like NumPy and tensors. PyCylon is not in the middle of all aspects, but it can be used in all aspects of data to enable high-performance data engineering and data movement in HPC clusters. Additionally, our data engineering kernels are exposed in Java and C++, and it can be used to reinforce existing data engineering workloads from big data community and HPC community. We discussed how PyCylon can contribute to data engineering. Now let's focus on the core architecture towards a Python API. Core of our compute and communication kernels are written in C++. Here the bottommost layer is the communication layer currently being enforced with OpenMPI. And we support both TCP and InfiniBand transports. On top of this layer, the network operators used are all-to-all, broadcast, reduce, and barrier. Since we provide the support as a library, compute kernels also support single process computations. These are labeled as local operators in the diagram. The data representation used in Apache Arrow-based columnar format. The relational algebra operators like join, union, intersect, and difference are also supported. We recently added group by and aggregation operators. We also support Apache Arrow-based data loaders, which are later being abstracted by deep learning data loaders. Currently, we support PyTorch data loaders. On top of the core framework, we expose compute kernels in Python via Cython bindings. We are currently expanding our Python API towards a rich data frame and a rich data series API. Let's discuss the data conversion and usability in PyCylon. We currently support CSV, pandas, and PyArrow data structures as data inputs. After a computation on kernels, data can be extracted as a PyArrow table, a pandas data frame, a NumPy array, or a CSV file. To provide better usability, we also integrate with IPyParallel to provide distributed computing capability on Jupyter notebooks. This is a work in progress for better usability for data engineers. Up to now, we discussed the core of Cylon and some of the use cases that we are going to discuss right now. Let's take a look at a sequential program. Here, PyCylon can be used as a library. So what we'll be first doing is import the CSV reader, table, and Cylon context. Cylon context is responsible for holding the context for distributed computation and sequential computation. Then user can write arguments taken from the terminal or user config files. And then we can pass this argument to create Cylon tables. Once you have the Cylon table, in a table you can just say join, union, or any relational algebra operator, and then pass in the join configs. In this example, we'll be doing an inner join by using sort algorithm, and we pass the left column as 0 and the right column as 3. Now you know how to write a sequential program in PyCylon. Let's focus on how to write a distributed memory program in PyCylon. The difference between a sequential and a distributed program is the way context being initialized, the way files are being loaded, and the way the join function is being called. Here the Cylon context is initialized with the config MPI. We currently support MPI, so you can just specify it as a string and we internally handles all the communication. Here, before loading data, if the data is split and each process is loading a unique file, you can specify the rank and load the data in such manner. Once the tables are loaded, you can just call distributed join instead of join and pass the same join configs. And when running the script, you have to specify MPI run and -n number of processes, then Python script and arguments. Now let's focus on some of the performance comparisons we did with PyCylon. Before going there, these are the software packages that we use. Here we compare the performance of PyCylon against Spark in two formats, with PyArrow support and without PyArrow support. And we use pandas with sequential program, Dask, and Modin. And here for Modin, we use the Ray backend to run the distributed examples. And if we take a look at the process we used Intel Xeon process. And we ran the experiment across 160 processes in 10 nodes. And the experiment we ran here is an inner join with 200 million records per relation. As you can see from the figure, PyCylon and PySpark are scaling much better than the existing Python data engineering frameworks. This was one of the expectations from the experiments, that big data systems are doing much better than the existing Python data engineering solutions. But the improvement of PyCylon is even providing a better solution than PySpark. Now let's focus on the Cylon performance with language bindings. Here we are going to compare PyCylon and JCylon with C++ compute kernel Cylon. Here we use the same Intel architecture and ran the experiments in 8 nodes with inner join and 200 million records per relation. As you can see, the overhead in language binding is very minimal. And we conducted the experiments across multiple nodes for different number of processes. One of our observations from previous experiments is that PySpark and PyCylon scale much better than the existing data engineering frameworks in Python. Now let's take a look at large-scale experiments conducted on PySpark and PyCylon to see how they scale. To this experiment, we used 200 processes across 10 nodes, And also we use the same inner join, but we use 10 billion records per relation. As you can see, PyCylon is doing significantly better than PySpark for the experiments we conducted. Cylon is an open source project. You can read the website or take a look at the GitHub repository. All the codes and benchmark codes are already in the GitHub repository. And these are some of the Cylon contributors. In this discussion, we mainly focused on data engineering on relational algebra operators. But high-performance compute kernels are also important in reinforcing existing Python codes. Number and Python provide user-friendly interfaces for such tasks. Also, frameworks like PyComps along with DiskLib provide distributed computation for data engineering. From the current discussion and the experiments we conducted, we draw these conclusions. PyCylon is a fast and scalable backend that can be either used as a framework or library. And the most important thing with Cylon is the capability of providing high-performance compute kernels and communication kernels that can be exposed in different language bindings. Currently, we support Python and Java. And the capability of having these language bindings allow us to seamlessly integrate with existing data engineering libraries in both Java and Python world. In this research, we focused on the Python ecosystem. And also, the capability of Python bindings provide the seamless integration between machine learning and deep learning frameworks. To conclude this presentation, let's focus on the future work. Cylon is an evolving project. In Cylon, Python is one of the key products for the data scientists and data engineers. And improving Python ecosystem is one of our key goals. To do that, we'll be integrating UCX to provide efficient communication kernels, and also extending our support towards existing data engineering frameworks like Modin and Dask. We'll be trying to integrate to their backends and provide support as a library. And also expanding the CPU computation towards GPU computation, we'll be trying to integrate with RapidScuDF. And also to improve the integration among two ecosystems, we'll be using Cylon as a backend to accelerate Twister 2. Twister 2 improves the performance of big data processing applications in the big data world. So Cylon will be playing a major role in improving that part. And finally, we'll be adding more applications to enforce the usage of Cylon for data engineering and data analytics. Thank you everyone for joining our presentation. Now we are open for questions.